To tackle Newton's law problems, the first thing is read the question carefully and then draw a diagram, a big enough diagram, a neat enough diagram, so that you can put numbers, put arrows, and all those things in it, and still be, readable. And after this, drawing the diagrams, draw the forces acting on it. Draw all forces acting on each object. Because you may have more than one object. If it is just one object, focus on drawing all the forces on that object. If it is more than one object, then on each object, draw all the forces. Is that clear? And if a force is known numerically, put that number down there. So you don't have to don't write mg as the weight. Now, if you know m and g, put the number there. All right, so labeling is an important thing. So labeling, yes, you call W and then write equal to, what is W? Mass times gravity. So take the mass times acceleration due to gravity, take the values, get that number, put it down there. Now, if you know the tension, then put the tension numerically. Otherwise, put it as a variable. Now, on one string, you're going to have a single tension. Suppose there are two different strings, you've got to call them T1 and T2. Right? You can't just use the same T everywhere. And after you draw these forces on each object, you may have situations where the first law is applied or the second law applied. And it depends on the situation. When is the first law going to be applied? Constant state of motion, which is either at rest or moving at a constant velocity. If something is moving at a constant velocity, use your first law, which is the net force should be zero. And if the net force is zero in a certain direction, if the net force is zero overall, you can clearly understand that that particular net force won't have an x component or a y component. If the net force is zero, it won't have an x component or a y component, right? If one of these components exists, can the net force be zero? No. So that is one condition that we apply for an object that is not moving or moving at a constant velocity. The net force will be, so for first law, net force will be equal to zero. That implies the net force in the x direction is zero, and the net force in the y direction is also zero. So those are conditions that you can apply. The net force in the x direction must be zero, as well as net force in the y direction must be zero. Especially if the forces are at angles, then what do? You resolve them, right? And then after you resolve them, you find the net x directional x components and equate it to zero, net y components and equate it to zero. And that is the application of the first law. Now for the second law, you're going to use net force is equal to ma for each object. Now if there is only one object, then it should be much easier. But if there are multiple objects, you may have to set up multiple equations and then finally solve them, right? And once you set up those equations and solve them carefully, you will get all the unknowns that they're looking for. Is that clear? So we'll go through multiple examples, and you're going to pretty much do the same thing. Drawing a diagram for that particular situation, draw the forces acting on each object, don't miss any of them. And when I say forces, it could be tension, it could be the weight, it could be the normal reaction, it could be the friction, it could be a component of the weight. And so many things can happen. And all those things must be marked. And then you will see how Newton's laws can be applied. Now, they won't specifically say you're going to apply first law or second law. You have to look at the situation and then decide. Okay? Now let's look at some situations. We did already a problem on connected systems like that. Now, another problem is probably this. This object, you must have seen that in your homework probably. Yeah. Well, there are different kinds of problems. This is a block, let's say, of 10 kilograms resting on a surface which is frictionless. If it is totally frictionless, and then this object is going to roll over a pulley, and there is another object connected here, and this object is 2 kilograms. Now, so that's a diagram. I've drawn just the diagram describing the situation now. All this will be given probably in words. An object is resting on a horizontal frictionless surface, and a string connects it through a pulley to an object that is 2 kilograms in mass that is hanging freely at the other pulley. So something like that. So that's hanging freely. So you set up the drawing according to your understanding, and then start. What is the next one? Draw all the forces. Now, do you know the force that is acting downward here?
Gravity.
Which is 2 times 9.8, 19.6 newtons. And that is basically the weight. 19.6 newtons downward. And what else is acting on this? Tension acting upward. And then we move on to this object. As the string is exactly the same, the tension that is pulling this object forward is also T. And this object has a weight downward, which is equal to 98 newtons, correct? And what else is acting on it? The normal reaction. Yeah, don't miss anything. Some of them may not be required in your problem, but still, just follow the steps and do everything according to this. So normal reaction is also 98 because this block is neither going down or up, and it is vertically at rest. Right? Vertically it is at rest. So we already applied kind of Newton's first law right there. Why is this equal to this? Because it is vertically at rest. It's not moving vertically into the table or jumping out. So we have this. Now, looking at the numbers, you got to also decide something before you start off. That is, all right, so these are the forces acting on it. This is 10 kilograms and there is 2 kilograms. Which way do you think the system is going to move? This way or that way? To the right or to the left?
To the right. Would it not move?
No, it's frictionless.
Oh.
It's going to the right. How can you think of this one moving to the left, carrying that object? Practically, that is impossible. Practically, think of that. You have something sitting here, like this book is sitting here, let's say frictionless, and you're connecting it through a pulley down to another object that is pulling from there, and this book strangely starts pulling that up. That is logically incorrect. So therefore, you have to put your mind straight and then say, all right, this thing is not going to climb up this way. It's not going to lift that up. That is wrong in terms of physics. So you know that this is going to accelerate that way, and that one is going to accelerate downward as well. So we understand that it is accelerating because there's nothing else holding this object. So it has to accelerate. So immediately what you do after this, what you do is set up the equations. And this is a much easier question because setting up the equation is so easy. Look at this one. Which is bigger? This is bigger than tension. That's why it's accelerated. So 19.6 minus tension is equal to MA, which is 2A. So we are using net force equal to MA. Now, why am I using 2 here? Because the object in consideration is a 2 kilogram mass. We are not taking everything into account. So one equation is set up there. And in this object is acted on by a tension forward, 98 upward, 98 downward, nothing this way. So what's the net force? T. In other words, T minus nothing, which is basically T. So this one's equation is T minus nothing is equal to MA. So in other words, T is equal to 10A. T is equal to 10A. This is the simplest of all problems. T is equal to 10A. Now you just add them up. Just add them up. Plus t and minus t goes off. So 19.6 is equal to 12a. And what is a? 19.6 over 12, which is 1.63. Everyone is doing it? 1.63 meters per second square. So if I release the system from rest, it's going to slide like that with an acceleration of 1.63 meters per second square. Get it? Now, I'm just developing the same problem. So this problem is over. Acceleration is that, and substitute that over here, then the tension is how much? 16.3. Substitute this in here. So you get T is equal to 16.3 newtons. Substituting this A into this equation, you get the answer straight away. So in other words, this is pulling it down with 19.6, and the tension is pulling it up with 16.3 only, and that's why it's moving down. And for this object, the forward force is only 16.3, and that's why it is in motion. Okay? Now, making some changes from being frictionless, I'm trying to get you some changes to the same problem so you will see what difference is coming out. Now let's say the coefficient of friction is 0.4. What will happen? If the coefficient of friction is 0.4, static friction, and the coefficient of kinetic friction is 0.3. What's going to happen in this scenario? When I release the whole thing, what's going to happen? Tell me how much is the frictional force. So redraw this problem, and then redraw this, and these things are pretty much the same thing, right? And over here we have this force marked, this force marked, this is marked over here. There's only one extra force that's coming in, which is friction. Now we don't know much about what is going to happen, because all we know is, yes, there is friction involved. Now, is that kinetic friction or static friction? We will find out. We will find out. Now, how much is the static friction?
39.2.
How much?
39.2.
39.2. So there's a 39.2 pulling from here. And how much is the overall pull by this little object? This is 39.2 pulling it backward. How much is this pulling with? So what is going to happen? Nothing. It stays still. Is that understood? Now let's think about kinetic friction. How much is kinetic friction force here?
29.4.
That is also bigger than this. And there's no chance of this object to be on the go or at rest. On the go or accelerated. So these are both impossible. Is that right? So what's going to happen to the object? Stays at rest, correct? Now when the object stays at rest, how much is the friction force acting here? Let me see if you are smart enough to get that. How much is the friction here? Yes?
0?
Not 0. Yes?
19.6.
19.6. It is,
Third law.
huh?
Should it be third law?
Not necessarily third law. What did I say about static friction? What's the smallest value of static friction? Is static friction always mu s times normal reaction? That's a maximum. That 39.2 is a maximum. What's the static friction between the book and the table right now? 0. So static friction can be 0, can grow as per need, but there is a limit for it to grow, right? And that limit is called the limiting value of static friction, which is what we calculate as 39.2. So you can hold it up to 39.2 max. And after you cross that threshold, immediately it drops down to what is known as kinetic friction. So in this case, even the kinetic friction is what is it, 27 point? 29.4. The 29.4 is also not going to be able to, this is not going to fight even the 29.4. And therefore the object is definitely not moving at all. So since the object is not moving at all, what is the acceleration of this object? 0. That means what is tension? 19.6. Because if this thing is not moving, Newton's first law says the net force should be equal to 0. So this is equal to this. Get it? So tension is 19.6. If this tension is 19.6, this one is also 19.6. So this block is now acted on by 98 down, 98 up, 19.6 backward. So how much is this friction going to grow up to? 19.6, and that's it. Because there is no more effort than 19.6 pulling this block to the right. And therefore the friction need not grow more than 19.6. It will reach 19.6 and it will just hold it there. Yeah.
Why is that resting?
Because friction, the maximum friction is 39.2. And the effort that is actually being applied on this side is only 19.6. And so there's no chance of that 19.6 taking the lead over this, 39.2. Okay? So 39.2 is a maximum. Never think that there is a force of 39.2 in this direction, always. Well, if that's the case, what's going to happen? Tension is 19.6, 39.2 this way, this object is supposed to go that way. Practically not. Right. Did you understand this? So yes, you're going to use the equation Fs is equal to mu s times normal reaction, but understand that equation is used only when you are trying to find the limiting value of static friction. The static friction grows. I have given you the graph already, I'm still putting it out here. The graph of static friction goes up like this, all the way till here, and then drops down to a new value when it is starting to slide. So this is the applied force. Applied force, and this is the friction. And this thing over here is the Fs, which is the maximum static friction, the threshold, the maximum value of static friction, and that is mu s times normal reaction. Only that, not any of these. None of these are actually given by that equation, only that. Only that one is given by mu s times nr. And this is when it is sliding, so this is Fk, and that is what is given as mu k times nr. Make sense? Good. Alright, so now, can I take it out? Now I'm going to change the values here to, let's say the coefficient of kinetic friction is 0.05. The kinetic friction coefficient is 0.05. I'm not even mentioning static friction because this indicates that it is already moving. This indicates that it is already in motion. Okay? And why do you think so? Because find out how much is the kinetic friction here? Mu k times
4.9.
mu k times, so this is 4.9. So this is 4.9 newtons. And how do you get 4.9? It is mu k times the 98. This Fk is mu k times normal reaction, which is 0.05 times 98. And that is 4.9 newtons. That is the frictional force on this object while the object is sliding. Now, since it is sliding already, it could have an acceleration. So now start working it out once again. There is possibly an acceleration. Let's find out that acceleration in the presence of friction. So you're setting up the equations once again. So 19.6 is bigger than T by MA. That's your first equation. And looking at this, tension, we are expecting it to accelerate forward just like that one. So tension should be higher in that case. So tension minus 4.9 is equal to 10A. So write it down, tension minus 4.9 is equal to 10A. Adding the two equations, we get how much? 14 point?
14.9.
Huh?
14.9.
14.7? 14.7 is equal to 12a. So a is 14.7 over 12. And that is going to be a smaller acceleration than when it was frictionless. 1 point. So you can see the presence of friction is actually creating an acceleration which is less than when it was frictionless. When it was frictionless, it was like easy to slide off, but now it is difficult to slide off. Now, if the coefficient of friction is too much, then it's not going to slide off at all. Say, take for example this book. If I connect a string through a pulley and put a small mass, this book is not going to move at all, because the amount of frictional force that this book is already having on the table, it's not going to let it go. Right? The maximum frictional force that this book can offer is maybe 15, 20 newtons, and then it's not possible to have a smaller object kind of drag it down. You need a bigger object, obviously. So how we tackle Newton's law problems is by just drawing the diagram, putting the forces down, and remember this frictional part of it. It's not a frictional frictional part of it. The frictional part should be handled with care. That's why I gave you that example. So it doesn't mean that you just throw the numbers straight away into that equation, mu s times nr is the friction and so on. You have to use your brains as well. Okay? And you go practically into the situation. And then you'll be able to understand that in the previous situation, this was pulling in 19.6 unsuccessfully, which means the friction was beating it by applying the same 19.6. And that was somewhere, it's not gone to the highest point yet. Okay. Now, in the homework and all that, you see they're connecting to a bucket, and they're asking how much sand should be poured in, and so on, right? So for that, what you do is, okay, then given the mass of the bucket, but just take the whole mass as m, and then you work it out. Find out m. That's the unknown, because they give you everything else. Since they give you everything else, just find out m that is needed to just get it sliding, right? To just get this one sliding, how much m should be involved? So what friction will you use there? Static. Static friction. So like in this situation, you're going to use 39.2 because that was a maximum. And for 39.2 to exist here, how much should be the pulling force on this side? It should be something or more, right? So you're looking for the minimum amount of sand that will set it in motion. So you just find out the m, that's the mass of the bucket and sand together, knock off the mass of the bucket from whatever you got, that will be the amount of sand, the mass of sand. Is that clear? So if you have not done it, you do it and then you'll see what I'm talking about. Now, inclined surfaces. That's pretty important. Inclined surface. Not all surfaces are going to be horizontal. You can have inclined surfaces, like your ramp. You can have inclined surfaces such as this. We call it inclined plane. This is an inclined plane. Now what is happening with the inclined plane? Okay. What is happening with the inclined plane is, if I'm putting an object here, now the object is sitting there. Is there an attempt to slide this object forward?
Yeah.
What is pulling it this way?
Gravity.
Gravity is supposed to pull it down. Gravity is supposed to pull it down. So what is pulling it this way? What is like if you're sitting on a ramp and you just release the brakes of the car, will the car roll down? What is taking you down? If gravity is supposed to take you straight down, what is that? Huh?
Inertia.
Say it again.
Inertia.
Inertia. It should be force. No. Something is taking it down. And you can see it now. If I increase this angle, you'll see it finally doing that. Right? What is taking it down? If you say gravity and you know that gravity is acting straight down, that won't be correct. Okay, so let's discuss more about this inclined plane so that you will be able to tackle problems with inclined surfaces. So, here's an inclined surface. And the most important thing in inclined surface is this angle of the incline. For a horizontal surface, obviously the angle is 0. And for greater and greater inclines, the angle is the one which is going to change. So that is an angle. So if you put an object here, if you put an object there on the inclined plane, what forces are acting on that object? Just tell me the forces acting on the object. Which way? What else? There's a normal reaction. How much? How much? Is it mg?
No.
No. It's not mg. What other forces are acting on it? Yeah, if it is not moving, yes, you can bring in friction. If it is not moving. But if it is absolutely a smooth surface, then friction is not coming in. So let's not bring in friction right now. We will bring it as we go on. So what are the forces acting on this object, which is freely sitting on an inclined surface? Is there any more forces? There's no more. Just these two forces. Just these two forces. Now, since it is sliding down, we understand that it has no way to go into the incline or up that way. So what we do is we split this mg into two components. We are going to resolve it into two components. And normally we used to resolve it into horizontal and vertical, right? Now see, this is a different kind of resolving. We're going to resolve this mg into two components. Which two components? Perpendicularly down this way. In other words, you just look at this whole picture like this with tilted head. So this is not your horizontal now. Think of that way. This is your horizontal and that's your vertical. Think of it for a moment that way. And then you can actually see that this has two components. Where are the two components? One is this. One is that component. By the way, if this angle is theta, what is this angle? Theta? Really?
No, 180 minus 90 minus
90 minus theta?
Oh.
Because this is a vertical and that's a horizontal, so it should be 90 here. So if this angle is theta, this angle must be 90 minus? If this is 90 minus theta, what is that? Theta. Good. Again, if this is theta, this is 90 minus theta here. And because this surface and this are at right angles, if this is 90 minus theta and this whole thing is 90, this must be theta. Make sense? Everyone's okay? Because you're going to do the same thing for most problems. So 90 minus theta is here and that is theta. Alright, so this is theta and that's mg. What component of mg is acting in this direction? Yeah, what component is acting? What component of this force is acting in this? Now this side, is it opposite of theta or adjacent of theta? So what do you use? So it's mg cosine theta. You know why I put mg cosine theta? Because we are looking to split mg into two components. One is this way, which is adjacent of theta. So it's mg cosine theta. And the other component is this component here, or this component here. Same thing. These two are exactly the same. I'm trying to split this into two components, one here and one here. And this component is basically the same as this. So what is this component? its opposite theta, which is mg sine theta. So this thing here is mg sine theta. Makes sense now? This is going to be there for all inclined surfaces. You're going to discuss, you're going to just take it exactly like this. So, is this object moving into the incline or out of the incline? Is this object moving? Stop. Is this object moving into the incline or jumping out? Neither. Neither. Right? So it is sitting there. It is sitting there. It is not breaking the meter stick and going down, or it is not flying away from there. In other words, there are two forces acting on this block in this direction, One is NR and one is mg cosine theta, and the end result is it is sitting there. Which law? First law says what? If this is sitting at rest because of two forces, those two should be? Those two should cancel. So what is the normal reaction? mg cosine theta. That is a normal reaction. So if you want to find the normal reaction on an object sitting on an inclined plane, the answer is mg cosine theta. It is not always mg. In the previous problems, we just straight away took it as mg. The weight acting on this book is 98, therefore the normal reaction is 98. Yeah, that's right. But when it comes to inclined planes, you don't jump to that conclusion. The normal reaction is the weight's cosine component. And what is taking you down? What is this force that takes you down? A component of the weight, don't say weight. So what is taking your car down the incline or down your ramp? A component of your car's weight. Do you get it? Or if you're sitting on a bicycle on a slopey road downwards, you don't have to pedal, right? You just sit on it and just release, and you'll start speeding down. Now, why is it speeding down? What force is taking you down? Is a component of the weight, and specifically the sine component of the weight. So mg sine theta is the answer for that. What is taking you down an incline? Mg sine theta. So what happens to the sine theta? Watch what's happening. What happens to the sine theta? What happens to the sine theta component as we start increasing the angle? It is increasing because sine theta initially is 0, right? Because 0 is, sine of 0 is 0. So there is no effort on this object. There is no effort on this object to take it that way, because mg sine 0 is 0. But when the angle increases, is there an effort on this to take it down? This is mg sine of that angle, whatever be it. If it is 30 degrees, then mg sine 30, which is basically half of mg. So when I keep it like this, there is a force acting on this trying to take it down, which is equal to half its weight. But when I increase the angle further, then it is going to increase. This downward thing is going to increase further and further and further. So when you have this going up like this, suppose the angle is 90 degrees. What is the force with which it is planned?
mg.
It is mg. You get it? The force with which it is going to fall or slide along the incline is going to be mg itself, because we have reached 90 degrees. When we reach 90 degrees, it is not even sitting on it. So what is the component of mg that takes it straight down the incline? Is mg. But when it's like that, it is just a component of mg, but a strong component of mg. The smaller the angle, the component is going to be smaller and smaller. You get it?
Yeah.
Now let's look at the normal reaction. When this thing is sitting on a horizontal surface, what's the normal reaction?
mg.
The angle is 0. The normal reaction is mg cosine theta. And what is cosine 0? 1. So what is the normal reaction right now? Mg cosine 0, which is mg itself. That's what you have done in the previous problems, right? What is the normal reaction? It is just mg. Why? Because the cosine 0 is 1. But when you incline it now, when you have an inclined surface, what is the normal reaction? It's mg cosine of some angle. Is it going to be stronger than mg or weaker than mg? Weaker. That means this incline is not pushing on this object as strong as it was pushing it when it was horizontal. So the normal reaction has decreased because cosine theta's value goes down as the theta goes up. Cosine 0 is 0. Cosine 90 is? Sorry, cosine 0 is 1. Cosine 90 is? 0. So when I increase the angle, this is barely sitting on the incline. It's barely sitting on the incline. The force that this incline is offering on this object is very small. It's small, small, small. Now what? With what force is the inclined surface
0.
pushing it that way? 0, because it is not even touching it. So the normal reaction becomes 0 when the angle reaches 90 degrees. Is it clear? So as soon as you have a problem where you have an inclined surface, immediately split it up into two components. That's mg sine theta, that's mg cosine theta. That implies that the normal reaction is mg cosine theta. And then keep working from there. Is that clear? Now let's put this into a problem. Let's see how this kind of works through a problem. So now we have an inclined surface. And the same object that was sitting there is sitting here, 10 kilogram object in the first question I gave you, right? That same object sitting here, and I'm having the same pulley, and the 2 kilogram object is here. It's the same problem, but now it's inclined. It's inclined. And let's say the angle of incline is 60 degrees. The angle of incline is 60 degrees. So, just like how you did your problems earlier, you're going to work it out the same way. And let's keep the coefficient of friction as 0.05 as before. What do you do first? Mark the forces. This force downward is?
90.
And then we have a tension upward. That's all we know on that side. Now let's come to this. What are the forces acting on this? Tension is acting that way. And there is gravity acting straight downward. So I can just put it like that. How much is it? 98. But more than this, we are interested in its components. We want the components more than anything else. So what component of this is acting in this direction? Down the incline. 98 sine 60, which is what? 98 sine 60, which is 80? 84 point? Everyone is doing 98 sine. 80?
84.9.
84.9 newtons is the force this way. And tension is acting that way. And now, what is the normal reaction? It's going to be 98 cosine 60. So this is going to be mg cosine 60. So the normal reaction is 98 cosine 60. 98 cosine 60, 49. Which is 49. So there's a normal reaction of 49. Now, what do you think is going to happen? You've got to make a guess first, and then work through the problem with your guess, but make that guess an intelligent guess. Don't blindly, make a guess. Just try to make an intelligent guess. And then, based on the guess, you keep working, and if all of them are coming out as expected, then you're right. Now, if you make a guess, and after that things are turning out negative, then your initial guess was wrong. Right, yeah.
So the 10 kilogram will pull it down there.
Now this is going to go this way. Previously it was sliding that way, but now you can anticipate like, look at this force. the downward component of the force of gravity is a lot compared to the little pull that this is doing here. And therefore, you can intelligently guess that this is going to accelerate like that, and this is going to accelerate upward. We will see if that assumption or if that judgment is right or wrong. Yes?
We're going to assume there's no friction.
No, friction is there. Now, which way is the friction depends on which way is planning to move. So we are thinking right now that this is going to slide this way. So where is friction? Which way? That way. In the previous problem, because we anticipated this to be moving that way, then we put friction backward. Friction always opposes the motion. So therefore, yes, there is a friction involved. And how much is friction? How much is friction? Because we're talking about kinetic friction right now. So mu k times nr. What is nr? 49. It's only 49 now. All right, so how much is it? 0.05 times 49 is 2.45 newtons. So the friction is 2.45 newtons in that direction. So we marked all the forces. We have marked friction, we have marked the downward component, and we already used this 49 in our friction calculation. And we have marked everything. What do you do next is to set up the equations. So which of these two is greater? The tension is greater. Tension minus 19.6 is equal to MA. That is just using the net force is equal to MA concept, because we are talking about acceleration. And then I'll come to this object. There is a component of gravity pulling it downward on the object, which is also 49. And that's why the normal reaction is 49. So this thing is not going to move this way, correct? So our focus is on this way. So we have to only include the forces in this direction, because this is net force is 0 anyway. This side, net force is 0. But this way, net force is not 0 because it's accelerating like this. So which one is greater?
84.9.
84.9 is greater than all the others. So our equation is going to be 84.9 minus t minus 2.45. That's it. Equal to MA. Yeah.
Why is friction 2.45?
Friction is mu k times nr. And mu k is 0.05. And nr is 49. The new nr is 49 because they're sitting on an incline. The normal reaction is 98 cosine 60, and that is 49. So multiply those two, you get 2.45. So now we have the equation. All the forces that are trying to drag it downward because it's accelerating like this, minus all the others acting the other way, equal to, add them up. You can knock off tension straight away. If you add them up, tension plus T and minus T is gone. Now what is 84.9 minus this? Good. 84.9 minus 19.6 minus 2.45. What is all that stuff? 60? 62.9 is equal to 12A. So what is A? Yeah.
5.24.
5.24 meters per second squared. So this thing is going to accelerate really this way. And since your answer comes out positive, you say, all right, my judgment was correct. It was actually going this way. Now, if you did it the other way, then the friction will be marked backward, right? And then you'll finally find out that the answer is coming out negative. Acceleration turns out negative. So if the acceleration turns out negative, it won't be the same number anymore because your friction direction was not the same. So you will get a negative answer implying just this fact that you have made a wrong judgment, and that is right there. And so you just correct your false judgment, and after that work it out once again. You can't just get a negative answer and say, oh, so it's positive. No, you can't do that. It'll be wrong. Why it's wrong? Because there's friction involved, and the friction is something that changes direction according to your judgment, right? If your judgment was it's going this way, friction is marked that way. If your judgment is going to accelerate that way, then friction is going to be the other way, supporting this. So therefore, any questions on this? How we tackle Newton's law problems? Yes? Okay? Clear? Yes.
Is the test due Saturday?
Sunday night.
Sunday night.
How many questions are on the test?
Suppose there's a rope tied between two walls. So the rope is there. And a boy hangs on the rope on the middle. So I have to draw the situation here. So the rope is definitely going to sag a bit, and that's a boy who's hanging on the rope. Now when I say hanging, not by the neck, okay, by hands. He's just hanging, like that. So these are his hands. All right, so for a diagram, you don't have to really draw the boy and all those things. That is enough. This is a diagram. And I said this is a midpoint, so it's kind of even, right? So the two ropes on both sides, and he just hangs onto it, and then just suspends his own body right on it. So it's going to sag like this. And let me tell you that this angle here is 20 degrees. The angle there is 20 degrees. So the sagging is 20 degrees below. And the boy weighs 60 kilograms. The boy weighs 60 kilograms. So a 60 kilogram boy hanging from a rope like this. Question is this: what is the tension on the rope? What's the tension on the rope? The question is, what is the tension on the rope? So now we have to start. Well, the drawing is already there. What do you do next? Forces. Go ahead and mark the forces. So the forces. One force that is acting here is 60 times. How much is it? 588 newtons. And we don't know the tension here, so let's call it T1. And the other tension here, let's say T2, we don't know.
They're not the same.
We can't jump to conclusions. We have to prove if needed. It may be the same, but you never take something like for granted and say, oh, that should be the same. Now, if you're trying to make some judgments, you always have a proof. So I don't know, so I'm just taking it as T1, T2. No, don't guess anything straight away. You may be right. You can guess something and get it right, but when you're working something out, you work it out fully. Now, the focus is basically on this hand over here. The hand is gripping on the rope. So the object that is acted on by forces is pretty much this. So his hands are pulling this down with 588, and there's a tension of 588 here as well, right? So his weight is 588, therefore there is a tension pulling him up with his hands of 588, and his hands are pulling this knot or the junction at 588. Is that okay? Now our focus is going to be on this, on the place where he's holding the hands. So our focus is only this, not any of this. So what is the boy doing? He's pulling this, the rope at 588. Okay? Now, is this part of the rope, is that junction in equilibrium? Yes. Or is it accelerating? It's not accelerating. It is in equilibrium. Correct? So since this is in equilibrium, we have to apply what law? First law. Because the first law says when an object is in equilibrium, which means it's at the same state of motion or at rest, net force should be equal to 0. So now we have marked all the forces. We have to now find out, I told you this, when the net force is 0, I told you that the net x force must be 0 and the net y forces must also be equal to 0, right? Is that okay? So now what I'm going to do is I'm going to split each of these forces into the y and x components. So you can do this, x and y components. You know how you resolve vectors, like that. What is what is this one's x component? What is this one's x component? What is T1's x component? You know when you split T1, you have two components, one like this and one like this?
T1 cosine 20.
T1, yeah, say that. So T1 cosine 20. But which way?
Left, left.
So what do you write here?
Negative.
Minus T1 cosine 20. Mark it that way. Now what's the y component of T1?
588.
No, I don't know.
Oh,
No, y
sorry. I meant
T1.
that. Yeah.
So it'll be T1 sine 20. Is that right? So y component is T1 sine 20, positive or negative?
Positive.
Positive. Now similarly, I'm going to split this into two components. I'm going to split T2 into two components. Alright, here is the x component. How much is this? T2 cosine 20. Now why I told you to draw a big enough diagram is to put all these things inside. If you make a tiny diagram, you will find it so difficult to put things inside. So this is positive or negative? Positive, right? So positive T2 cosine 20. And what is the vertical component of that? T2 sine 20. I'll put T2 sine 20. And so we have taken care of T1 and T2, and there is a force here of 588 pulling which way?
Down.
And that is vertical or horizontal? X or Y?
Why?
It's Y. So it's minus 588. And this one doesn't have anything X. Right? Now, since I said the net X force must be equal to 0, when you add this up, it should become 0. Net Y force must be 0, so when you add this up, it should be also 0. And that's why we're saying this, see? Net of all the X forces must equal out 0. Net of all the Y forces must also equal out 0. Only then the net force will be equal to 0. Is that clear? So especially when you know it's in equilibrium, Newton's first law comes in. So if this is equal to 0, so add them up. T1 minus T1 cosine 20 plus T2 cosine 20 is equal to 0. What does this mean? That means T2 cosine 20 equal to, when you flip it that way, T1 cosine 20. And what do you see here? Cosine 20 and cosine 20 is gone. What do you see there? We see that T2 is equal to T1. So we prove it. We don't want to take, make it, kind of take it for granted. You just want to prove that. You have proved it. So T2 and T1 are exactly the same, and so I can call it T. Just one tension. Now go back there. Set up the conditions again. Write down the conditions for that side, which is T1 sine 20 plus T2 sine 20 minus 588 equal to 0. Got it? Now, since we already proved that T2 and T1 are the same, which is T, I'm going to remove the T1 and T2 and just put T. So T sine 20, and T sine 20 minus 588 equal to 0. What does that simplify to? 2T sine 20, and then move this one that side, so it's 588. Can you find T then? Or I can divide both sides by 2, and you can see how much it is. So finally, what is T? So 588 divided by 2 and divided by sine 20. How much?
1.6.
400.6?
100.
No way. 800 something, yeah.
859.
8?
859.
I don't know. Make sure it's right.
First.
Right?
860.
860? 860 newtons is a net force. No, not net force, the tension. So the tension here and here are far more than the weight of this boy. And this is the other kind of problem where you have equilibrium.